This program is a presentation of UCTV for educational and non-commercial use only.
So it is my distinct pleasure to introduce to you now Zhongkong Zi. He is our invited guest. Dr. Zi graduated from Zhuhao Medical College in China and then attended Nanjing Medical University, where he did his anesthesia residency. He started his research career in Wayne State University in Detroit, Michigan, and he obtained a PhD in pharmacology there in 1994. He went on to Harvard Medical School to do further postdoctoral research training in both human and animal behavioral research. He began an anesthesia residency at Massachusetts General Hospital, and after completing his clinical training, he's devoted his work to the link between anesthesia and neurodegenerative disease. And he was really one of the primary investigators to make this initial link between, for example, the possibility that there's a link between Alzheimer's disease and other neurodegenerative disorders with anesthetic exposure. He's currently an associate professor at Harvard and an attending anesthesiologist at the Massachusetts General Hospital, and he's the director of the Geriatric Anesthesia Research Unit at MGH. So welcome, Dr. Zi.
Thank you, Dr. Yang, and thank you, Dr. Mays, for the invitation. It's a great honor to be here, and I truly enjoyed the talks in the first half. I'm looking forward to more talks in this second half. So today I'm going to report to you our studies following our initial studies regarding the potential upstream mechanism of how the drug called isoflurane can induce the apoptosis and Aβ accumulation. So I'm very glad to ask Dr. Marcus a question regarding this Aβ hypothesis, because I'm going to mention that here. So even with some debate, many people are still thinking that this Aβ hypothesis is the foundation for the Alzheimer's disease neuropathogenesis. Basically, the imbalance between the Aβ generations and Aβ clearance or degradation is like a hallmarkers for these pathology changes. And apoptosis, even though some debate regarding whether apoptosis has been contributed to AD, but still many evidence to suggest apoptosis may also play a role in there. However, due to the long duration of AD process and the rapid clearance of this apoptosis marker from the cells, sometimes it's difficult to identify the classic marker of apoptosis in vivo in the brain of AD patient, which have left the debate. But there is increasing evidence to suggest the contributions of Aβ for Alzheimer's disease neuropathogenesis. So why we study this? Because basically findings suggesting that surgery and anesthesia has potential associated with persistent cognitive dysfunction. Although the cause of the dysfunction is unclear, but recent studies suggest that isoflurane, which is one of the most commonly used inhalation anesthetics, can promote the cascade activation, apoptosis, and Aβ accumulation and aggregation. Well, this is a concern because we know that accumulation of Aβ is a hallmark features of this Alzheimer's disease. So in our lab for these years, we study the 4 of commonly used inhalation anesthetics like isoflurane, sevoflurane, desflurane, and nitric oxide. And so far, we have found isoflurane can increase apoptosis and the Aβ accumulations in cell culture models, animal models, and even in some human studies. And sevoflurane increased apoptosis and Aβ in cells and animals. And so far, the desflurane and the nitrous oxide using clinical relevant concentration has not been shown to induce any damaging things on the cells, and we have not done this in animals or humans. So this is our early study to suggest that as compared to the control group, the isoflurane, 2% for 6 hours, can induce the caspase-3 activation as compared to the control group. And furthermore, we found this 2% isoflurane for 6 hours can also increase the Aβ generation for both Aβ40 and Aβ42 as compared to the control treatment. And we did some tunnel studies to showing that as compared to control, isoflurane treatment can increase the number of the tunnel positive cell, suggesting that isoflurane can not only induce caspase activations, but also the apoptosis. So from here, we pretty much see that, okay, this drug is maybe toxic, maybe can induce this apoptosis and Aβ accumulations, and these things are associated with Alzheimer's disease. So the question that if we can find the potential target for the upstream mechanism, maybe we can find some intervention to prevent this isoflurane-induced apoptosis and accumulation of Aβ. So the question we want to ask is that what is the upstream mechanism of isoflurane-induced apoptosis and Aβ accumulation? So our early studies, we did some work to show the potential pathways. And I'm not going to go into detail for this, but I'm going to just report to you what we found. And we found potentially isoflurane can induce caspase activation and apoptosis. And from here, they can increase the levels and activity of beta secretase and gamma secretase. And these two enzymes are the primary enzyme for the generation of Aβ. So when this enzyme activity increased, we're going to see the APP processing was promoted, and we're going to see the increase of Aβ generation. Furthermore, we found Aβ generation can coming back to potentiate this isoflurane-induced apoptosis to form a cycle. So isoflurane, apoptosis, base increase, gamma increased, the APP processing was promoted, the Aβ was generated, and the Aβ coming back to potentiate more isoflurane-induced apoptosis and to form another cycle. On other pathways, we also found Aβ can be aggregated by isoflurane treatment. And this Aβ ligamization and aggregation can also induce caspase activation and apoptosis. And we know that this one coming here to have more Aβ generation, which will coming back over here to form another cycle of this isoflurane-induced apoptosis and Aβ accumulation. So this is our early studies. Now following that, we have a question. So that is how this happens. How isoflurane can trigger caspase activation and apoptosis. So we did some further study to have these pathways, potential pathways, which is isoflurane may act on this MDA receptor, also IP3 receptor, and SACA from this target to increase the calcium levels in the cytosol. When the cytosol calcium level increase, we may see some damage of mitochondria. And mitochondrial damage, we may see caspase activations and apoptosis. So we published the data before. Then our next question is that how this happens, how the enhanced isoflurane come here to enhance calcium level can damage the mitochondria, and how can causing this apoptosis. So I'm going to tell you some detail for our recent studies to address this question here. So this is our hypothesis pathway, which is suggesting that isoflurane may trigger apoptosis through this mitochondria-dependent pathway. And we hypothesize that isoflurane may working on the BCL2, which is the anti-apoptotic factor, and BEX, which is a pro-apoptotic factor, also aspirin may affect the ROS accumulations to causing mitochondrial damage. When this happens, and may showing some cytochrome C release from the mitochondria, then causing cat9 activations and 3 activation, then apoptosis. So let's go there step by step. So we're first using the Western blot in the H4 human neuroglioma cells, which is the culture cells. We found that azathioprine 2% for 6 hours can enhance the level of BEX, which is the pro-apoptotic factors. And this doing the quantification also showing that as compared to controls, the azathioprine, which is 6-hour treatment, for 2% increase the level of BEX. We then found in same cell culture studies, we found 2% azathioprine for 6 hours can decrease the level of BCL2, which is the anti-apoptotic factors. So the quantification is showing that, again, azathioprine decrease the levels of BCL2 in the cell culture studies. So we're following with this RS imaging studies. So the right panel here is mitochondria staining, and here is RS staining, and the third column is a merged graph. And the top one is the control studies, and the bottom one is the azathioprine treatment. Again, it's 2% for 6 hours. So as you can see, as compared to the control treatment, the azathioprine, can we see here? That's okay. So from my screen, I can see that as compared to the control, we have more green stuff here, showing that showing that the ROS was enhanced following azathioprine treatment. But we don't know it's inside or outside the mitochondria. So we're doing some. We merged that. We found some yellow part, which you cannot see here, of course, which suggesting that this ROS increase is inside the mitochondria. So green plus red equals yellow. But don't worry, we have a ELASA study to further showing that azathioprine treatment can increase the ROS levels as compared to the control study. Interestingly, we also did study using Bepta. Bepta is a drug which can decrease the silyl calcium levels. And we found when using Bepta, we can decrease the azathioprine-induced ROS generation. So suggesting that this ROS generation following azathioprine treatment may be associated with the silyl calcium levels triggered by azathioprine treatment. So from here, we can have a hypothesis that azathioprine may be working on BCL2 and BX and ROS accumulation to causing potentially the mitochondria damage. Then we found when this damage happens, can we see some release of cytochrome C from the mitochondria? So again, we're doing some imaging studies. This is the mitochondria imaging controls for staurosporine, which is our positive control in our studies, and azathioprine. So this cytochrome C was the green one showing cytochrome C was inside the mitochondria. This is nuclear staining. So focus on here. So everything inside the mitochondria will be the yellow part, or covered by the blue. But we did see some green spot, which is outside the mitochondria. Why outside? Because if the green is not merging with red, it should be still continue to be the green. So this showing that staurosporine can increase the release of cytochrome C from mitochondria to cytosol. And same thing to azathioprine. And after following azathioprine treatment, we see some release of cytochrome C from mitochondria to cytosol. And we also performed some Western blot, and again, we're showing that as compared to the control treatment, the azathioprine increased the levels of cytochrome C in the cytosol. And again, the quantification of the Western blot confirming that azathioprine can increase the levels of cytochrome C. So here we continue this hypothesis pathway that is for the mitochondrial damage, we see the increase, the release of cytochrome C from mitochondria to cytosol. Then we found acetylfluorine treatment can enhance the activation of caspase-9 and caspase-3, but not caspase-8. So suggesting that it's, the acetylfluorine may focus on this mitochondria-dependent pathway to trigger apoptosis, not the death receptor pathways. To confirming that, again, our apoptosis is indeed following Cas3 activation, we did tunnel studies to suggesting that acetylfluorine induce more tunnel positive cells as compared to the control treatment. Interestingly, in our early study, we found that desflurane is a good guy. It did not trigger apoptosis and Aβ generation, and we don't know why. But the study here using the 12% desflurane, which is kind of equivalent to acetylfluorine concentrations, also the clinical relevant concentrations, we did not see the changes in terms of Bex levels, BCL2 levels, and ROS generation, cytochrome C release, caspase-9 or caspase-3 activations. So showing maybe mitochondria is a target in terms of different effect of acetylfluorine and desflurane. So again, about studies suggesting this, that acetylfluorine may trigger apoptosis through this mitochondria-dependent pathway. But as we mentioned that desflurane did not, acetylfluorine does. So we try to see that whether mitochondria can be part of this upstream mechanism of acetylfluorine-induced apoptosis. So why targeting mitochondria? Because that mitochondria dysfunction and energy metabolism deficiency has been shown to very well correlate with impairment of cognitive function in Alzheimer's disease patient. And we're interested in this MPTP. It's a mitochondria permeability transition pole is an transient increase in the permeability of mitochondrial memory. And MPTP has been well shown to be associated with this apoptosis. Therefore, we have interest in this MPTP. So has been shown that studies showing that MPTP has how to cause apoptosis. MPT has been shown when MPT open happened, it can cause a decrease in this mitochondrial memory potential, which will leading to the reduction of ATP generation. And calciums, BCL2, BX, and ROS are all associated with this MPTP opening. And we also have to mention that cyclosporin A and 2-APB has been shown is a blocker for MPTP. This cartoon also showing that when without MPTP opening, we can see have this mitochondrial memory potentials and has a normal ATP generation. And when this MPTP opener, we can see that decrease of mitochondrial memory potential and decreased ATP generation. So from here, we try to using the flow cytometry and also using these kits, try to study whether acetylfluorine is an MPTP opener. How the kits work? So we're injecting a drug called calcium AM, and this drug inside cells can be metabolized by the enzyme in the cells to degrade to calcium. The calcium will light up every apartment in the cells, the cytosol and the mitochondria. So the cell will become very bright, which can be detected by our flow cytometry. Then we're giving another compound called cobalt. The cobalt can go inside the cytosol to quench it, to reduce the lighting of calcium here. But cobalt cannot go inside the mitochondria without the opening of MPTP. So for control cells, when we're giving both the calcium AM and cobalt, you're going to see the partial lighting of the cells because mitochondria still light up. Just like in this room, this room still light up, but outside is dark. That's control cells. But if you're giving any medication which can open MPTP or which can increase the cytosol calcium levels, it will trigger the opening of MPTP. When MPTP opening, the cobalt can go inside the mitochondria, go into this room to quench the lighting of calcium. That time, the cell become totally dark. So from here, we first showing our positive control, which is indomycin. Indomycin can enhance the cytosol calcium levels. When that happens, the calcium will go into the mitochondria to open the MPTP. So let's go slowly here. So the black graph here, which is identical with indomycin, is our totally control. It's unstained BO104 cell, which is the red neuroblastoma cells. When we're giving the calcium, the calcium will light up the cells. Then this red line showing the calcium effect. So it's light up, it's on this side. So this side is light, this side is dark. When we're giving the cobalt, which is the blue curve here, we see the decrease of lighting up cells. So the curve shift to the left a little bit. The cell become a little bit darker. But when we're giving calcium, cobalt, and indomycin, things are different. The indomycin open the MPTP, then the cobalt can go inside the mitochondria. The whole cell become totally dark. So come to almost like original starting position. So again, the black bar is our total elective control, and the red graph here is our calcium without cobalt. And the blue bar here is the calcium with cobalt, which is only still the mitochondria lighting up, but the cytosol is quenched, it's dark. Indomycin will make mitochondria opening, the whole cell become pretty dark. So with this graph on mind, let's go to next graph, which is our osflorin show up. Osflorin is this green line here. You can see here it's just in between of indomycin, which is our positive control, totally open of MPTP, and this blue line, which is our calcium plus cobalt. So this slide showing us that osflorin may be a partially MPTP opener as compared to the indomycin. So that partially opening can make some mitochondria to have cobalt go inside to quench the lightness. Once more, this purple line and green line are both the osflorin treatment to in this flow cytometry experiment. So this slide showing that osflorin maybe is an MPTP opener in this flow cytometry studies. Interesting, we tried again 12% desflorin. We found desflorin is in contrast to osflorin does not shift this curve. It's identical with the black line and the blue line are almost identical, suggesting that it's no different in terms of the cobalt itself. So it did not open the MPTP, so the cobalt cannot go inside the mitochondria to do anything. And then we find that, okay, so maybe osflorin is an opener of MPTP, causing this apoptosis, and how to confirm that? So we found a drug, this cyclosporin A. As I mentioned before, cyclosporin A is the blocker of MPTP. So we'd like to see whether we can using cyclosporin A to changing the MPTP opening following osflorin treatment. So first, we found this 1 microgram cyclosporin A self does not changing the MPTP opening. Then we found this 1 microgram cyclosporin A can attenuate the osflorin-induced MPTP opener. So here is a very simple lines. So this blue line is our positive control indomycin. Again, it's totally dark of the cells. And these black lines in the middle is the osflorin treatment has partial opening of MPTP, the weak opener of MPTP. Then when we're giving the cyclosporin A, it can shift this curve from the middle to the right, suggesting that it's blocking the osflorin-induced MPTP opening. That's in the flow cytometry. What happened to if they can blocking this MPTP opener, can cyclosporin A also attenuate osflorin's induced apoptosis? So next, we did some Western blot in the same cell line, this red neuroblastoma cells. As you can see, cyclosporin A itself does not causing any changes of caspase-3 activation in the B104 cells, but cyclosporin A attenuate the osflorin-induced caspase-3 activation. So from both the flow cytometry studies And this Western blot studies, we found cyclosporin A can blocking acetylfluorine-induced MPTP opening, can also blocking acetylfluorine-induced caspase-3 activation in the same cell lines. So what about the in vivo relevance? So we move on to the mice, to the animals, and we found similar situations. So this 9-3 is acetylfluorine only, can causing caspase-3 activations. 4 and 5 is a mice following with the pretreatment of 10 milligram per kilogram cyclosporin A. It can attenuate the acetylfluorine-induced caspase-3 activation. Finally, we found acetylfluorine can also decrease the ATP levels in this in the H4 human neuroglioma cells. So remember, we talked about the when MPT opening, we should see the changes of mitochondrial memory potential and ATP reduction. And we have not done any study for the mitochondrial memory yet, but we did see the decrease of ATP levels following acetylfluorine treatment. So from here, we have another hypothesis for the pathways, and we're thinking that acetylfluorine may be by opening MPTP to decrease the mitochondrial memory potential, causing reduction of ATP level, which will causing the mitochondrial damage, and then the cytochrome C release from mitochondria to cytosol, causing this pathways or the mitochondrial pathway of apoptosis, leading to cytotoxicity. But we do not know at the moment any involvement of BCL2, BAX, and calcium and ROS in this potentially acetylfluorine-induced opening of MPTP. So that's a question we need to answer, and hopefully we'll have some answer quick for the potential regulations of these modulators for acetylfluorine-inducing MPTP opening. So for conclusion, we found this commonly used inhalation anesthetic acetylfluorine may induce apoptosis through this mitochondrial pathway of apoptosis. And acetylfluorine may increase cytosolic calcium levels, leading to apoptosis. And acetylfluorine may causing apoptosis by opening the MPTP. And when apoptosis happened, which can increase Aβ generation and accumulation. And these increased Aβ levels will coming back to induce another round of apoptosis and Aβ generation and accumulation. So I'd like to thank many people in my lab to perform that, particularly Laurel, who is the person doing this, a lot of these mitochondrial studies. And Dr. Rudy Tanzi, who's my former boss and very good friend of mine, has been always give us a stimulation idea regarding these studies. Thank you very much for your time.